So the final speaker of this morning session will be Rene Vidal from Johns Hopkins University. He's going to talk to us about how to use differential equation in dynamical systems in order to understand and accelerate optimization algorithms.
Good morning. Thank you to the organizers for inviting me. It's a pleasure to be here. So as George said, one of the aspects in deep learning that is very important is to do optimization. There's a lot of mysteries as to why one can solve very large-scale optimization problems using very simple methods, such as gradient descent and extensions. And we've done a lot of work trying to understand the landscape, global optimality, and questions of that kind. This is a slightly different type of work trying to understand the algorithms and, in particular, acceleration mechanisms that have been proposed in the literature. In particular, I think the basic idea is the following. The idea is to begin with some optimization problem and look at the iterates of the optimization algorithm and take the continuous limit, and that would give rise to a dynamical system, differential equation. And perhaps by looking at the dynamical system using techniques from controls, such as Lyapunov stability, we're going to be able to understand better things such as the convergence rate of that algorithm. The second part, which is what you can see here at the bottom, is once I have a dynamical system, sure, I can use it to understand the algorithm I started with. But perhaps I can take that continuous system and discretize it. As it turns out, different discretizations might give rise to different algorithms. And maybe I can come up with algorithms that didn't exist before. And so this process of generating new updates and new algorithms is another very exciting area that is being investigated. So this area is by no means new. This is one of the first examples, 1847. So you begin with an optimization problem. What you do is, for example, let's say you're trying to understand gradient descent. So the new x is equal to the previous x minus some learning rate times the gradient. You can easily see that if you take the difference and divide by that and take the limit as eta goes to 0, you're going to get the following differential equation, which is the classical gradient flow, and that was studied by Cauchy. And as it turns out, you can look at the convergence rate of gradient descent. This is, say, for convex functions and for suitably chosen step sizes. And so the convergence rate would be 1 over k for that discrete algorithm. And if you analyze the differential equation, you get 1 over t. So this is what we mean by matching rates of convergence. Now, Nesterov, around 1983, proposed a different algorithm that is really like gradient descent. So you can think of it as, this is like gradient descent. But notice that instead of the x, I've got x hat. And so this x hat is sort of the accelerated variable, which is really the same as the x except for a velocity term with a weighting factor that is kind of very carefully crafted. And this is one of the most used first-order methods today because the convergence rate is 1 over k squared as opposed to 1 over k. And that's the optimal rate you can achieve for convex problems. And the interesting thing, though, is that while this was a super smart and very simple tiny modification, the question is, why does it achieve 1 over k squared? And can I use the same principles for accelerating other methods? And so that was not very well understood up until recently. And so there was this work by Su, Boyd, and Candes, where they actually took the continuous limit of this discrete set of equations. Now you get a second-order differential equation. Notice that it's time-varying, and the time-varying comes exactly because this is also time-varying. And they also analyze the convergence rates, and in the continuous system, you also get 1 over t squared. So another example of this matching rate of convergence. So what my student or postdoc has been doing is, how can we extend this? So these results required the function to be smooth. They were designed for problems that are unconstrained and, by and large, gradient or accelerated gradient-based methods. So what we've been doing is, first, how can we relax the unconstrained assumption? So we have looked at methods such as ADMM and various extensions of ADMM and trying to derive what are the differential equations using Lyapunov stability to analyze convergence and derive convergence rates. The second one is, what about non-smooth? Many problems in machine learning require you to use ReLUs, max pooling, or L1 norms, and so on and so forth. So it's important to also understand how the methods perform in the non-smooth case. And I'll touch very briefly on that. And the last one is sort of the last step, which is, can I go back? If I have a dynamical system, how do I discretize it? And you can clearly imagine that not all discretizations are good. Do you want to preserve stability? You might want to preserve other properties. And so symplectic integrators is one class of methods for discretization that happens to work very well. And we've been using tools from physics, such as relativistic energies, to derive new optimization algorithms, in particular these relativistic gradient descent that I'll be talking about. Okay, so let me begin with the constraint story. So suppose you've got an optimization problem like minimizing f plus g, and then the variables x and z are related by a linear transformation. So in this case, you can look at one well-known algorithm called ADMM, and you can derive the differential equations associated with ADMM by taking continuous limits. And the important observation is that it looks pretty much like what you would have in the standard case, except that it's modified by the A matrix that is the one with the linear constraints. So under the extra assumption that that matrix is full rank, then you still get a valid differential equation. If this was not full rank, you will get a differential inclusion. So that's the reason why we have this extra requirement. You can do the same thing for accelerated ADMM, and you get exactly the same kind of differential equation of Boyd and Candice, except again for that weight that comes from the A matrix. And using tools from Lyapunov stability, you can derive convergence rates. And for ADMM is 1 over k and 1 over t. And for the accelerated version is 1 over k squared and 1 over t squared. Interestingly, this rate wasn't known before. And so, and again, these rates are derived sort of independently. The analysis for the discrete algorithms is different from the analysis for continuous algorithms. So you're just showing that you have matching rates, but it's not the case yet that the continuous analysis tells you something about the discrete analysis. So just to give you a little bit, for those of you who are in controls, which is probably the vast majority, simple things from controls can be used. So for example, you can take, you can show that let me go back. You can show that if you take the objective, if you make assumptions of continuity, differentiability on the objective, and full rank, as I mentioned before, then a strict local minimizer is asymptotically stable. So that is easily done by constructing a Lyapunov function. The second one is the derivation of the rates. Effectively, the theorems are of the following form: the objective at x of t, where x of t is the solution to this differential equation, minus the objective at the optimum is less than or equal to a constant divided by t. So that's what I mean by a convergence rate of 1 over t. For the accelerated method, you can do something that is very similar, and you can show the stability. Now you have two variables, x and x dot. The equilibrium point now is the minimum and 0 for the velocity. And notice that I've got the word stable here. So for some technical reasons, you cannot prove asymptotic stability of this second order equation. You only get stability. You need to assume a little bit more about the objective function in order to get stability. And again, the same type of result is obtained for the convergence rate, 1 over t squared. Okay, so what about the non-smooth case? So what we've been able to show is that the same type of analysis and continuous limits arise. The key difference is that instead of having x dot equals to something, you have this inclusion, because now, say, the subgradient is a set. And so the technical issues that arise now is that you no longer have a differential equations. The solutions might not be unique. So how do you do the analysis and the stability? So there is, fortunately, a lot of literature on differential inclusions. So we've used it to analyze this type of differential inclusions and, again, derive the same type of analysis, that equilibrium points are stable or asymptotically stable, and that you get matching rates of 1 over k or 1 over k squared depending on whether you're using the original ADMM or accelerated versions. And this can be extended to many other algorithms. This is what is known as relaxed ADMM or relaxed accelerated ADMM. Sorry, let me go back. Relaxed ADMM, relaxed accelerated, this is the known as heavy ball algorithm. All of them have differential inclusion. All of them come with stability analysis and rates. And this is just a table containing all of the rates that we've been able to derive for all of these variants of ADMM algorithms. So just to point out very briefly, here you see 1 over t. You see also that the singular values of the constrained matrix play a role in the constants. You see that in the strongly convex, the mu parameter is the constant for the strong convexity. That also plays a role. Okay, so that was the first part, which is, can I begin with an optimization problem, look at the algorithm, take continuous limit, arrive at a continuous dynamical system, and can I analyze the dynamical system to derive convergence rates and things like that? So what I'd like to do now is the other way around. Can I begin now with a continuous dynamical system and come up with new algorithms, or can I come up with properties for existing algorithms? So the way we do that is by looking at a particular class of dynamical systems. These are Hamiltonians, for which we can have good discretization techniques, symplectic integrators. But because we want convergence, we need to make some modifications to classical Hamiltonians. So in particular, you can see here that what we're going to look at is the following. This is the classical Hamiltonian, so this is the kinetic energy, and this is going to be the objective function that I'm trying to minimize, f of x. This would be the equations in blue. The blue part would be the classical equations of a Hamiltonian, but we're going to make that modification where we do some dissipation with a rate gamma. That dissipation is sort of critical, and that is what's going to give us a convergence rate that is going to be strongly related to gamma. So this type of Hamiltonians have a name. They're called conformal Hamiltonians. And their interesting observation is the following. If you look at what's known as this two-symplectic form, which is just the wedge product between dq and dp, again, p is sort of the momentum variable, and q is the state. So then this symplectic form is going to decay exponentially when you've got this dissipativity, and the rate of decay is exactly the dissipativity that you add. So in classical Hamiltonians, this symplectic form is preserved. So you would have W of t is equal to W0. So this decay and that dissipativity is sort of essential to get the results we're going to have. So there is this notion of being conformal symplectic, which really means the following. We're going to take these continuous equations, and we're going to discretize them. So here's what you see. Q of k plus 1 is a discretization of q. Likewise, p of k plus 1 is a discretization of p. So the idea is that the symplectic form in the discretization is also going to satisfy identically the same equation as in the continuum. Okay, let me repeat maybe the high-level picture as to why we're doing this. You have a continuous dynamics, and let's say that it has some convergence rate. What you want to do is to discretize it, and when you do so, you want the resulting discrete system to be stable, to preserve the critical points, but you want to also preserve the convergence rate. And if you go ahead and discretize using in a naive manner, those properties might not be preserved. So what is really happening here is that you're trying to come up with a property which is to preserve, quote unquote, the symplectic form that would allow you to get the convergence rates being preserved. In other words, what you're trying to come up with is a discretization of the continuous dynamics such that the solutions to the discrete equations closely follow those of the continuous, and therefore the continuous dynamics are preserved. So going back, that's exactly what's said in here. H is going to be the discretization, the step size, and gamma is again the same gamma that shows up there. So with that in mind, you can apply it to classical mechanics. And so this is the classical Hamiltonian here. And these are the classical equations. So m is the mass in here. And let's see what happens. So you go ahead and discretize it, and you get some set of equations. Okay, so this would be the symplectic integrator applied to a classical dynamical system. And now you just do a tiny, teeny change of variables. This is the change of variables. You change the mass by the step size, and this would be very well known for those of us in controls with discretization on classical linear systems. And magically, you get the classical momentum algorithm, which is one of the heavily used algorithms these days in optimization and in deep learning in particular. So the first observation is that classical momentum is a symplectic integrator applied to the classical Hamiltonian. And therefore, the convergence rates of classical momentum can be analyzed because of the convergence rates of the continuous system. Okay, and that's exactly what's here in this next slide that says that classical momentum is a conformal symplectic integrator. Interestingly, you can look at one of the other most famously used methods in deep learning, a Nesterov accelerated gradient, and you can look at the iterates, and now you have what it means to be symplectic. And you can prove that Nesterov is not. So that's an important distinction between momentum and Nesterov, that one is symplectic and the other one is not. But then you can become fancy and say, aha, I can take the kinetic energy, and instead of using classical mechanics, I could use relativistic. And so you can change that. So C here is the speed of light right now. M is, again, the mass of the particle. And now you can derive the Hamiltonian equations for this relativistic system. Okay? And now you can discretize it using the symplectic integrators. And you can arrive at a new optimization method that is neither Nesterov, not classical momentum. It's a new algorithm that we call relativistic gradient descent. And interestingly, there is a normalization step. This is, I don't think it's exactly related, but it's very close to the normalization that is done in adaptive systems, which was done in the controls literature more than 30 years ago. And again, because this is a symplectic integrator, you can immediately know that things such as convergence rates of the discrete system are the same as those of the continuous system. So these are some synthetic examples of comparing these methods on some simple, in theory, because the number of variables is small, but these are fairly non-convex optimization problems that typically people struggle with, and just comparing different optimization methods here. So this is gradient descent, so that's the blue curve. This is the x-axis is the number of iterations, the y-axis is the value of the objective in logarithmic scale. So gradient descent is pretty much stuck. These two are Nesterov accelerated gradient and classical momentum. And this here is this new relativistic method, which is, as you can see, incredibly faster. It also goes up and down, as you can see. This is another objective, so the same behavior. In this particular case, again, relativistic gradient goes down much faster. This is another example where we took a 3-layer neural network and we trained it by minimizing the standard loss, the cross-entropy loss on MNIST. And now what we're doing here is to compare, again, these various algorithms. So what you can see is these are training errors, and this is testing errors. This is the loss value, and this is the classification error. So again, when you look at this, the blue curve corresponds to classical momentum. The red curve corresponds to ADAM. ADAM is another very used technique in deep learning. And again, this relativistic gradient descent comes at the bottom, showing that it converges faster. This is now the classification error, which is not always related one-to-one to the optimization error. And you can see that the classification error also goes down much faster using the relativistic method relative to the state-of-the-art methods used in deep learning. So to summarize, what we are trying to do is to put together dynamical systems and optimization. This is a very old field since the 1800s due to Cauchy. And there are two major directions. The first one is, can we take optimization problems and analyze them by analyzing the continuous system? And the second one is, can we take continuous dynamics, discretize them in a faithful manner, and get new optimization algorithms with better properties? So we've been able to carry out that program for constrained methods, ADMM, for non-smooth dynamics. We've done all of that for splitting methods, for example. I didn't talk about that today. And I spent quite some time on this idea of symplectic integrators for doing the last part. So this is the work of Guilherme Franca, who is a postdoc in my lab, and in collaboration with a colleague in optimization and a colleague who does sparsity. And this is funded by a Muri project. Thank you very much.
Questions for Rene? Yeah, Mike here. So, wait, microphone.
So when we work with optimization algorithms in continuous time, the notion of acceleration is not very clear in the sense that, for example, if you just rescale the time, you can see acceleration in continuous time. So how would you comment on that? So that's the question that I have because I've been working on this as well.
Yes. So that's totally true. In particular, for example, in discrete time, the step size is very important, while in the continuous dynamic, that step size, you set it to 0, and it actually even disappears from the continuous dynamics. So what happens is, in this interaction between continuous and discrete, is that when you actually try to go back, you need to reinsert the step size. And the methods that would argue that in continuum you can go infinitely fast, when you do that, you lead in discrete time, it's unstable. So that is where this question of having tools that when you discretize, you are preserving the dynamics becomes very important. And so that's, I think, what is partially addressed by the second part of the talk. But my short answer is you're totally right, and one needs to be very careful when you go back and forth to get these matching rates correct.
There's a question.
I had a question about the relativistic gradient descent. It's derived, as I understand, with a very nice analogy with relativistic mechanics. I'm surprised that it performs so well. Can you maybe comment on why it's so much faster than, let's say, accelerated methods? And how do you pick the speed of light in this?
Yes. So let me go back, perhaps. So very nice question. So we have not done yet the analysis of the convergence rates of the relativistic method. And we don't know whether, but we expect and we anticipate that it's probably going to be something like 1/k². And it's perhaps in the constants that appear in the algorithm that might explain the difference in performance. Now, this difference in performance, at least for the deep learning case, it's confounded with other factors. So for shallow networks, we see this behavior. For deeper networks, we're just doing the experiments this past week. It doesn't appear that there is such a big difference in performance, but that may not be pure optimization. Again, there is all of these overwhelming evidence and some theory that in deep learning, deeper architectures are easier to optimize, and therefore the algorithm might matter less. How do you set the speed of light? Indeed, this becomes now a parameter, and you can change it. And depending on how you tune it, you get different algorithms. In particular, if you let the speed of light go to infinity, that's one extreme case. If you let it go to 0, in particular, classical momentum emerges a particular case, depending on how you choose the speed of light. That's another reason why we believe that the convergence rates might be somewhat similar. But we haven't done fully the analysis, and tuning the parameters and tuning the speed of light is part of the tuning the parameters of optimization methods.
Okay.
So when you set the mass to the discretization, you set m equals h, and I believe the conformal mapping wasn't conformal anymore as h goes to 0. So essentially, as the discretization becomes finer and finer, the Hamiltonian does not remain conformal anymore, right?
That's not entirely
you're
clear.
not losing-
Maybe what's not clear is that there is a rescaling of the Q variables that goes here. So here you have to multiply by m and divide by h, and there is an extra scaling to get, for example, the classical momentum. Because otherwise, directly, you would have not gotten that m is equal to h. Yes, maybe we can discuss it. There is a little bit of extra step there.
There's another question.
Just one question on the relativistic method. Have you worked on applying that to the constrained case as well? Is that something that's ongoing?
That's something that's ongoing. In a certain sense, the constraint case is fairly general, but it's not based on a Hamiltonian. So we need to put the two of them together to do that.
Any other questions? Can you comment on what happens when you add noise?
Noise to what?
To the gradients.
To do stochastic gradient.
Yep.
We have not done the analysis, but we've got the expert here who did the analysis. In that case, you probably have stochastic differential equations. Typically, you have to look at the probability distribution. You get Langevin dynamics. So I hope that the things would be extensible, but
Okay.
that's his PhD thesis.
They are essentially mirror copies of this analysis.
Yes.
All right. Oh, one last question.
So there are several symplectic integrators for Hamiltonian dynamics, like symplectic Euler schemes or Sturmer or Verlet schemes.
Yes.
So these are found to be more better in performance, let's say in the context of Langevin algorithms. For instance, people would use leapfrog, or
Yes.
would it be, do you think it can work well in practice for this setup too? In your
Yes. So I skip, or I didn't say anything about the second part of my talk that was going to be about splitting methods. And so you're totally right, and this is maybe one particular example. You can see here that the flow is, in a sense, the sum of two terms. So what we have done is exactly to do that form of splitting. You can compute the flow for one, the flow for the other. And then what we've used to arrive at these ones in particular is the one particular type where you do half of flow one, full flow 2, and half of flow 1 again. And there is all of these techniques for symmetrization, and you're totally right. This means that there could be a much richer variety and classes of new algorithms. These particular ones that I presented today are based on just one of those splitting and discretization.
All right. This concludes the morning session. Let's thank Rene again.